Yes.
We push back or acids and bases keep homework?
It's due tonight, right?
Yeah.
No, I like it.
Why not? No,
Alright. There will be no debate. Alright. Reactions between acids and bases are called neutralization reactions. If a strong acid or base is involved, the K equilibrium will be greater than 1 and the reaction will go to completion. Because again, a strong acid or base would be involved. Okay? So yeah guys, today we are going to look at various cases when acids and bases attack each other and not just water. You know, in our previous lessons, most of what we looked at was one or the other attacking water, and then water would behave as the opposite thing, right? So if you have an acid attacking the water, what would the water behave as?
The base.
And if you had a base attacking water, what would the water behave as?
Acid.
The acid. Today, we're going to look at what happens when the acids attack each other. Now, that could happen a couple different ways. It doesn't necessarily just mean that, oh, HCl will attack NaOH. Because what do those things each attack first? What does HCl attack first before it even gets to NaOH? What's it in? What's it all? What are they all dissolved in?
Water.
So the HCl would attack water first, right? And really, what is its form? Instead of HCl, it's really going to be H3O plus, right? And what about NaOH? What happens when it attacks the water first? What's it going to make a lot of? OH minus. And then there can be a fateful encounter between what and what? H3O plus and OH minus. And what do those two make when they come together? And wait, hold on a second. They make water, and water has a pH that is
Neutral.
Basic.
and we call these
Whoa.
Basically.
So this is just a complex way.
Alright, so let's look first. Our first scenario of the day that we are going to look at is when a strong acid attacks
A strong base.
a strong base. So strong acids and bases both do what in water? They 100% dissociate. So then in reality the strong acid by proxy isn't really itself, it is really just a whole bunch of what? And the strong base isn't really itself, it's really just a whole bunch of. And so when you mix the strong acid and strong base, what are we actually putting together? H and OH. And when those come together, they form
Water.
H2O, water. And so the K equilibrium for this reaction is 1 times 10 to the 14. Oh my gosh, it's the same thing as KW, remember? Alright, so the other parts of these acid and bases act as, we've seen this word before, spectator ions.
Oh, I forgot.
Because they have their eye on you.
Reaction.
So guys, spectator ions, remember when we learned about net ionic equations? So the spectators are the ones that they don't precipitate, right? Or they don't change. So if you had a Cl minus before, because your H plus went and attacked water, after the whole reaction's done, is that Cl minus still going to be dissolved? Yes, therefore it is what we call a spectator ion. Yay, you're here. I had them text you.
What?
Yeah, I texted you.
I wasn't paying attention to my phone.
I was like, text those who aren't here. Let's find out if they're okay. Okay, so the pH, guys, here's the critical point for strong acid, strong base reactions. If you have an exact amount of both and they're the same, what's the pH going to be?
Wait, say that again?
If I have the exact amount of moles of both acid and base, strong acid, strong base, and I mix them together, what's the pH going to be? Neutral, 7. However, guys, Are they always gonna be exactly the same?
No.
So what you would do is take the one that is and subtract the one that is, and then whatever that one is, depending on if it's the acid or the base left over, you would take the negative log of it, and if it was the H plus, then you're fine. That's your pH, right? The negative log of H plus or H3O plus is your pH. However, what if it's the base that's left over?
You should do the negative log of the OH.
So you take the negative log and it gives you the POH.
And then for the POH, you find the pH.
And how do we do that? We subtract it from 14, yes.
Are you gonna do this stuff?
Yeah, I'm just trying to get it, like, because we already kind of know that. I'm trying to pull it out of you first, and then, yeah. So, let's do an example, guys. So, in this example, we have 250 milliliters of 0.35 molarity HCl is mixed with 150 milliliters of 0.50 molarity NaOH.
Ouch.
Write the net ionic equation for the reaction and find the pH of the final solution. Assume that the volumes are additive. So, ladies and gentlemen, first things first, here's our reaction, okay? And so let's think about what's actually happening here. So we're gonna split this up, that stays the same, and then we'll split this up, okay? When we do this, what do you guys notice about here and here? And what about here and here? What?
They cancel.
Well,
They don't cancel, but they're the same.
they're the same. So, in order to make a what type of equation would we cancel them out?
Net ionic.
Net ionic, and I think I heard it over here too. Excellent, guys. So, we're going to cross out a bunch of these, and bam, what are we left with? Our what equation? Our net ionic equation. Yes. Okay. So, here's our net ionic equation. Give you guys a second to write. What do you guys notice about these volumes? Well, they are milliliters, right? But what else do we notice about them? Are they the same?
No.
And are these molarities the same? Okay, so because both values are different, that means we're going to have to convert both of these into moles, right? We'll do that shortly, yes. Yeah, go ahead. All right, does anyone still need this slide? All right, let me advance. So we're going to find the excess reactant, and as you guys adeptly pointed out, we need to convert both these to moles. And as you guys also pointed out, these are not in our appropriate liters. So to make them liters, we divide both of these by what to get these two? We divided them by 1,000, right? And then remember, whenever they give you molarity, capital italicized M, molarity is the same thing as that number of moles over how many liters? 1 liter, okay? And what's this going to let us cancel out, guys? The liters, right? Now, which one of these answers is greater? The H plus. So when I subtract these, what is that answer going to be? Is it going to be H plus or OH minus? H plus, because it's the higher one, right? So we are going to subtract these two up here, and then of course it'll be H plus at the end. But before we can call it a molarity, what do I actually have to do with the volumes on the bottom? We have to add them because water doesn't just mysteriously disappear, right? So we have to have, the volumes are additive. We have to put the volumes together. So then once you've subtracted these two and added these two, we'll divide the answers, and that will give us the molarity of the H plus. Guys, are we done?
No.
What's the question asked for?
pH.
So what do I have to do with the molarity of our H plus?
Negative.
The negative log.
Is that what you two were going to say?
Yeah.
Okay, perfect. So I'll give you guys a couple seconds. I know people are still writing this slide, and then we'll move on to the next one. Oh, and actually, they squeezed it in down here. So guys, then we find the pH by taking the negative log of that answer, as you guys noted. Guys, a pH of 1.48 Is that acidic or basic?
Acidic.
Because it's below 7. Now, guys, pH is very helpful, but did we even need to calculate pH to know this thing was going to be acidic?
No.
Because what did we figure out looking at these two? Which one was going to be left over? Which one was going to be left over? The H plus. So by default, we know intuitively that it's going to be acidic. However, pH is great because it gives us an actual calculated number that helps us judge the relative degree of acidity. Yes, Victoria.
To find the POH, I forget, do you put it in negative log or 10 to the,
Whoa, from here or like in a problem where it calls for finding pH?
like in a problem calling the POH?
Oh, you just take the negative log of the OH
Oh,
concentration.
Okay.
Now,
And then
here's
you
the
subtract
tricky
it.
thing. If you have H plus, but it's like one of those weird problems where they want POH, then you would do this
Like
and then
add-
subtract it from 14 to get your POH.
Okay.
Like if you want to go in between the two.
When do you use the 10 to the,
That's when you're going the reverse direction. Solomon was actually asking me this morning. If you want to find the H plus, you would do 10 to the negative pH, and that would, like if you do, guys in your calculators, do 10 to the negative 1.48, it'll give you 0.033.
okay, thank you.
That's how you reverse it, and that's an important question to ask, because that is not on the reference sheet. Yes?
Okay, so like let's say on an FRQ, they ask us like let's say they're asking
Welcome
us
back.
if it was acidic or basic and like justify your answer. Could you just justify?
Yeah, you could have just subtracted these and said H plus greater
Okay.
than
so you don't
OH.
actually have to find the pH. to
Yeah,
justify.
although the pH is really nice,
Okay.
really nifty. Okay, guys, any other questions? Let's advance. So,
This way.
enough, oh yeah, yeah, go ahead. Guys, enough with the easy stuff. That was easy.
That was easy.
That was easy. Let's do some hard stuff. All right, let's do some hard stuff. And guys, when I say that, am I lying? What does it say right here?
That doesn't make any sense. That
So
explanation.
So it's like,
Why-
it's ironic. It's like we're doing hard stuff with weak stuff.
Yeah, but let me ask you guys a question. Strong, you literally just, like what we just did, you subtract stuff, you take negative logs, whatever, right?
Not this.
But when a weak thing is involved, that means you're probably gonna have to make what charts? Ice chart!
I hate
So
this.
weak acids and bases means equilibrium. Alright, now, there is a silver lining though. This isn't entirely guaranteed to be a bad problem, because what is the other component of this?
A strong base.
So, if the strong base outnumbers the weak one, will there be any weak one left afterward? Oh, so then we don't need to do icy stuff. So if your strong one outnumbers the weak one, then you don't need to worry about icy stuff. But if the weak one outnumbers the strong one, hey, welcome, sir. Did you get my message?
No, Guinness?
No, I had
Oh,
I
yeah.
had your boy message you.
Boy.
I had Edward message both of you.
Thank you so much. I'm here. I'm good.
Welcome, sir. Guys, can you guys confirm? I was worried about those two.
Yes.
What is it?
All right. So anyway, let's examine this, guys. Strong bases. Man, I love that sound. Sorry to interrupt. I just really love it. So good.
You're welcome.
Strong bases completely dissociate. Each OS minus or OH, not OS, OH minus rips an ion off an H plus ion off of a weak acid. Guys, isn't this such a vicious word? Rips. Such a vicious word. All right. So anyway, guys, what's interesting about this though is the weak acid. Guys, do weak acids dissociate very well in water? They don't, right? So what's interesting is the strong base in this case. Oh, see that, Ryan? The strong base in this case doesn't go after H3O plus like it did in the strong. Here, it's actually going to the source, the unreacted weak base or weak acid, and it rips the H off it, and in the process, it actually will create what? And this is important because in strong, the conjugates are all spectators, right? The Cl minus and the Na plus, those were just spectators no matter what. However, here, that conjugate is actually going to be a part of the net ionic equation.
So like, equals it.
The conjugate's actually going to be part of the net ionic equation. So let's examine the scenario.
Mr.
Equal
Wright,
volume, oh, yep.
So if we say had a weak acid base reaction, then you'd have.
Well, you said weak?
Yeah.
Oh, that's a whole thing.
Then
We're getting to
You
that.
have to use an ice trick then, right?
We're getting to that. And yes, guaranteed misery. Yes. Alright. So, equal volumes of 1.0 molarity HNO2 and 1.0 molarity KOH. Guys, are any of these strong? You should have like a spidey sense looking for that. Any of these strong?
The KO is.
Is KOH strong?
Yeah.
Yeah, because anything from group 1, except for H of course, anything from group 1 or CASRBA are all considered strong hydroxides, right? Okay, so that KOH is strong. What about HNO2? It's weak, right? What would the strong version of that be that we've seen before? HNO3. Okay. So write the net ionic equation for the reaction. Identify the aqueous species that are the highest concentration equilibrium. Okay. I promise one more thing before I actually do the problem, guys. That just opens up a great question. Could be a future free response question. Ladies and gentlemen, why is HNO3 a strong acid and not HNO2? What is the difference between them that could break the case? Let me see. Olivia, you want to give it a try?
Well, there's more electronegativity surrounding it.
Because of the extra.
Oxygen.
Yes. Is that what you guys were all gonna say?
Yeah.
Yeah,
the homework
so-
really helps, like,
Yeah, the homework.
It's over the
yeah,
file.
like,
I know.
I didn't think of electronegativity with this at all.
So the homework has its difficulties and eccentricities, but this is one of the good things about it. Good job, guys. All right, so let's advance into this problem. So we got our HNO2 and we got our OH minus. Ladies and gentlemen, why didn't I just call this H plus? Why am I calling it HNO2? Go ahead, Thomas.
Because the base is gonna rip off some of the hydrogen, so the NO2 is actually part of the net ionic equation.
Right, and because it didn't do what first in water?
It didn't completely dissociate.
It doesn't dissociate, so the OH goes in and it's gonna rip that H off there. And so like you said, the NO2 is actually gonna be a participant in our equation. So we've written our net ionic equation, and now they want us to identify the aqueous species that have the highest concentration. Guys, right here, this is a trick question that you're gonna see on the homework, but you're also gonna see it on the AP exam. They love doing this. Ladies and gentlemen, what did they tell us to first write?
The net ionic.
Okay, and by all accounts, have we done that correctly?
Yes. Yeah.
However, what is missing from this because it's a net ionic? I'm looking right here. What should go here, and feel free to look up at the question. What is missing from here that would be present in the complete equation?
K.
K, right? And where would the K go?
The 408.
Right here and right here. But we don't put it there because it's a what equation? Net ionic. Now, here's the tricky part. What did this and College Board and the homework, what did they specifically ask you for? But then they proceed, and this is insidious, to ask for which species have the...
Highest concentration.
Oh, so you need the K.
So, just because it's not in the net ionic, did we destroy matter? Is there no K here?
It just.
Well, there is a K there.
Yeah, I kind of hit you guys with the triple negative there, yeah. So, the K is there, and it should be one of the highest concentrations, because they've gotten 100%, right? So there it is, K plus, and then this NO2 minus will have the highest concentrations. Yes.
So the one arrow means like complete dissociation, and that's because we have the strong base, right?
Well, okay, so let me clarify. It's not only because we have the strong base, but it's also because what did they say right here?
Because of equal volume.
Equal volumes, yes.
So if we have a weak acid and a weak base, then
Again, we're not there yet. That's its whole scary, separate misery. Yes, sir.
Did I miss the explanation where you explained why potassium and NO2 have the
Yeah.
highest concentration?
Maybe sort of, but I wasn't done explaining it, so.
Okay.
So basically what's happening is, this the reason I call this an insidious question. They specifically asked you guys for what here?
The net ionic.
And so what's not obviously gonna be in the net ionic? The K. But what has to be for the answer to this question, the highest concentration? Because K is there, it's not gone, it's just K likes to dissociate. So it's there, but in ionic form. Alright, and then real quick guys, before I move on, why is NO2 minus there in the highest concentrations VIP room? Why didn't OH minus get invited down here? Let me have Michael.
OH minus is not there anymore. Well, okay, after the reaction, OH minus got mixed with the hydrogen.
So it's fully reactive.
Yeah, it's just the water.
And guys, does water have a concentration?
No, it's infinite.
Exactly. So there we go.
is it because it's a strong base and it completely dissociates?
Same, well, not dissociates, it like completely reacts.
Wait, why doesn't it completely dissociate?
No, it did.
Oh, it did.
But this is after that. This is when it attacks the weak acid after that.
Oh.
This is like post to what you're talking about.
Okay.
This is like another event.
Oh, so
Yes, sir.
is the reason why it's specifically K plus and NO2 minus is because K is the strong base and NO2 minus is the conjugate acid, which would also be strong?
So the reason the K is just a separate thing. It dissolved instantly from the strong base, which I
Yeah.
think is what you're saying. Yeah.
Okay.
And so K is gonna by default always be among the highest concentration. Now it can be a little dangerous, like looking at these. Sometimes the K won't be, like if this is like 0.5 or something like that.
Okay. That makes sense.
Yes, sir.
So NO2 minus is the highest concentration because it is the conjugate acid.
And because this goes all the way.
Wait, what?
Like this reaction here, this is a strong one. This is going to yoink it over here.
Oh, okay.
That's why it's the strongest.
That makes sense.
All right. Any other questions, guys, before I advance? All right, let's go. So another question. Ooh, here we go, guys. Is that good when I say that? Let's go. Equal volumes of 1.0 molarity H3PO4 and 1 molarity NaOH are mixed. Write the net ionic equation for the reaction. Identify the aqueous species that have the highest concentrations equilibrium. Ladies and gentlemen, is NaOH strong?
Yes, it's very strong.
Okay. Does this look right?
I mean, yeah.
No. Oh, it does.
Okay. What's going to be the highest concentration? Oh, I love it. You guys are already like you guys are triggered from the last question. You already said Na. Good job. And then do you want to add the other one? Oh, PO4 minus. Yes. Good job, sir. Good job, Daniel. Okay. So the Na plus and the H2PO4 minus will have the highest concentration. Do we all agree with this? This makes sense, right? All right. Are you guys ready for Bizarro Land?
Please hang on the slide for just a second.
I am staying on this slide for just a second.
That second's passed.
Okay, William.
What'd you get?
So basically, the way that you can figure this out is It's just, the stuff that has the highest concentration is gonna be the stuff that would normally be spectators.
Yeah, because they're not reacting technically.
Exactly, yeah.
Okay, that's
Oh my god.
But you guys see why I complain about this is because they try to trick you because it's nowhere to be seen in the actual, the net ionic.
yeah.
Because it's like a ghost, a spectator. All right, guys. I don't think you guys are ready for this.
Okay, so let's take a pause.
Good idea.
Guys, what's different? What's different?
NaOH is 2 moles.
Oh.
Why is it
So
equal
this
volume?
time around, we changed the concentration from 1 molarity to.
Icy?
Now, ladies and gentlemen, let's go back to this for a second. Let's go back to this. Let's go back to a world where everything still made sense, okay? Ladies and gentlemen, didn't we kill off all of the H3PO4s? We did, right? Because we had equal volumes of 1 and 1 molarity, right?
Yeah.
However, what did you guys notice? What was one of our products?
H2PO4.
Ooh, there's still some juicy hydrogens on
No.
there. So now that all of this low-hanging fruit has been taken, now we're going to go after the H2PO4 minus because we've got double the OH minus. So this time around, what are we going to form? Instead of H2PO4 1 minus, we're going to form HPO4 2 minus. So now what is going to have the highest concentrations, guys?
Still the same thing.
Still the Na, but what about this one? Is this the same thing?
Now it's a water.
What's that?
Never mind. I'm not
Go ahead, Daniel. You mean HPO4 2 minus? Yeah.
Okay, good.
All right. So guys, now it's the HPO4 2 minus. Oh, you guys aren't ready for the next one.
Wait, I don't even get this one.
Yeah.
What's
So
not
Hold
to
on.
get?
Give me a second. I gotta write it down.
I get the Na, right? Are you telling me that HPO4 2 minus is also a spectator?
Now, or not a spectator, it's a participant.
It's a participant.
Yeah, look at, let me, guys, stop writing for a second. I'm going back to the first one. So originally we made H2PO4 because we had equal of these two. But when you increase your NaOH, that NaOH now we have extra and it can go after this one. So it further, guys, what does it mean when we take off an H? It's called deprotonates. We further deprotonate it to make HPO4.
What happens if we have 3 molarity, not just 2?
You mean like? Oh wait, I thought I had it on the next slide.
That would have been cool.
Well, then it would have made PO4 3 minus. Yes, sir.
Could you explain why the Na is missing? I still don't get it.
It dissolves in water.
From which one? This one?
Yeah.
Edward, you know this. What did they ask for right here?
Mid-ionic.
And in net ionics, we take out the spectators. And Na is a spectator because it would be Na aqueous on both sides. Remember, in these, you don't have them, if they're on both sides and they're aqueous, then you can't have them in here. See, this one, H3PO4 aqueous, is different from this one. That's why they can both be here. And OH minus is different from H2O. That's why it can be here. But Na, if it was here and here, would be the same on both sides, so we have to cross it out.
Okay.
Yes, sir.
What is HPO4? Is that an acid or base?
HPO4 2 minus?
Is it an acid?
Well, that's kind of in contention, right? Because here, HPO4 1 minus, or H2PO4 1 minus, is technically the acid because the NaOH goes after it.
Okay. So the reason I'm confused is like, I just thought the conjugate acid would be one of the highest concentrations. So would so by that meaning would HPO4 be a conjugate acid or
No, it's the conjugate base.
conjugate base?
Because it was the acid over here, because this is the strong base pushing it
Oh
over.
yeah. Sorry, never mind. Conjugate base. Thank you.
Alright guys, So, let's look at some more reactions with strong.
Is it for me?
Hello, this is Mr. White. Hey, what's up?
Am I in trouble? I sacrificed myself.
7? Yeah, I can do that. Yeah. Yeah. I got you. What room is that?
Oh.
Okay, 7, and then I'll come down and get the key and the attendance. Okay. But
What teacher is it, Mr. White? Mr. White, what teacher are you replacing for the 7th grade?
Almadine.
Oh.
Should replace my 7th hour.
Alimony or
I
alimony?
thought he was like learning about.
Alimony.
Alimony?
Ryan,
Isn't
you wanna have
alimony?
Mr. White as our 7th hour teacher again?
No, isn't
You wanna
that
have
what
Mr. White as our
like
7th hour
alimony,
teacher
like,
again?
isn't that what people pay
That was
other people
amazing.
for them to stop on?
No, alimony is what, like when you get a divorce
Yeah.
and if one partner in the relationship made a lot more money than the other one, they charge alimony to the one who makes more to even them out.
Nice.
And it sometimes applies to the rest of that person's life.
Poor Jeff Bezos.
Alright, so let's examine this problem. So 20 milliliters of 1.5 molar KOH is added to 50 milliliters of 3.0 molar acetic acid, CH3COH. Guys, remember acetic acid, chaku, is what's in vinegar, okay? So acetic acid is vinegar, but vinegar is like 5% acetic acid, the rest is water. So we want to know, find the moles of OH minus added, and then we want to find the moles of CH3COO minus in solution. So guys, first off, what do we have to convert the 20 milliliters into?
I think it's
Liters. And how do we do that, Ryan?
by
Dividing by what to get from milliliters to liters?
1,000.
1,000. That gives us this 0.020 liters times. And then, guys, remember, molarity is the same thing as that number of moles over how many liters?
1 liter.
1 liter. And what is this going to let us do? Cancel out the
Liter.
liters. So then 0.02 times 1.5 gives us 0.030 moles of OH. Okay? So then, part B says, find the moles of CH3COO minus in solution. Well, that's not hard because, guys, is KOH strong or weak?
Strong.
It is, in fact, strong, right?
Yeah.
So, as a result, the moles of your OH added are actually going to equal the moles of CH3COO minus because that OH attacks what?
The H.
The H from here. So then all of that OH gets used up, and as a result, the OH you threw in there is equal to the CH3COO minus that is left over. It's like a conversion. It instantly gets converted to this one. Alright? Does everyone see why that is? It's because OH minus is considered a what base? Really, really strong. CH3COOH is considered pretty weak because it's not on our
Big 6.
big six. Therefore, we default to it being weak. Okay? So, guys, this is probably the hardest part of acids and bases. Not the math, it's the logic. You guys need to get good. GITGUD, get good. You need to get good at logic. Use your brain. Word problems are great in math, aren't they?
No.
This is why I'm taking critical thinking.
Oh, I did Wordle today.
I didn't do it yet.
Alright. No one spoil it. I got it in 5 out of 6 today.
I didn't know.
Fail me on the test.
I'm on a 9-day streak.
How much teaching? Is it too loud for you guys?
Yeah. Basically.
No, stay. Come on. Please. Sometimes I wonder why
It's
it's
like
not
a
here
full
willing.
hour and a half. I'm just yelling chemistry.
Well, it's because they're trying to take a quiz, that's why.
Oh.
It's normally not that
You
quiet.
should make it
but-
louder then.
What?
You should be louder then.
Nah.
Survival.
Okay, I'll try to be a little. Okay, so
You're just really good at
Can't
projecting.
hear you,
This is
Mr.
why.
White.
Yeah, you be a little louder.
So weak bases will instead of electrons from a strong acid. Alright, so our scenario here this time, previously it was weak acid, strong base. Now it's strong acid, weak base. Well, guess what? It's basically the same thing, but instead, it's basically the same thing, but instead we just flipped it around, okay? So instead of the OH minus being stronger, what's actually gonna be stronger, guys? The H3O
Thing.
plus. So weak bases may be nitrogen-containing compounds such as NH3, or the conjugate bases of weak acids. Guys, NH3 is one of our most famous, what type of base?
Something.
Weak bases. Man, it's so hard to not be myself here. Yes, sir.
Aren't the conjugate bases of weak acids supposed to be strong bases?
No, remember, it's like a slider scale. So when we introduced that, what you're talking about, we were saying that really strong, oh gosh, I'm getting too loud. Really strong acids have really weak bases. But then as you decrease the strength of the strong one, you increase the strength of its conjugate, like this. So there's a whole range right around here where weak still makes weak.
So it's like right in the middle.
Yeah.
So if it was just like a really weak acid that would make it strong. It just doesn't hit the threshold of strong.
Exactly. Okay, guys, let's look at this problem. Equal volumes of 2.0 molarity NH3 and 2.0 molarity HI are mixed. Write the net ionic equation for the reaction and identify the aqueous species that have the highest concentrations at equilibrium. All right, guys, so what do we notice about this scenario? What do we say right here?
Equal volumes.
And then the molarities are the same, right?
Why are we whispering?
Because I feel it. Because I feel attacked right now. Alright, so predict what happens here. Well, which one is strong? HI is strong, right?
Wait, no water's gonna form.
Well, oh, that's actually, guys, this is what Michael says. Michael, go ahead.
No water's gonna form.
Right, because this is one of those weird nitrogen bases.
Yeah.
Which, it's weird that we call them weird because they're very common. Okay, so here we go, guys. The H from HI is going to attack what? NH3, right?
Is it just gonna make like a bunch of hydrogen gas?
Why don't I have I in here, guys? Spectator, because the HI automatically attacks the water. Now that we know the net ionic, guys, tell me, what are going to be the highest concentration ions?
Where's the oxygen coming from? Where's the H3O coming from?
They put
Let's
a-
get a thin air.
the hydrogens on the okay. You guys, these are great. These are all great questions, and I'm gonna beat all you guys over the head, figuratively.
Wait, Mr. White.
What does it say?
I will have to continue taking this class.
What does it say right here, guys?
Molarity.
Things that have molarities are guaranteed to be dissolved in water.
That's
yes.
BS.
Yes. Yeah, go ahead.
That's BS, Mr.
Wait.
White.
It's assumed.
That's BS.
He was like, no water will form. I know you have water.
Oh, no. He's right. There's no OH though.
So it's not formed, it's already there.
Will water form or not?
You just never
It won't
left?
form,
No,
but it'll be there.
Listen.
A product.
Your white is really good.
No, what I meant was there's no water going to be formed from an OH uniting with an H plus. You are stripping an H plus from an H3O plus.
Water will be formed.
Yes.
That's the
So
way.
water is being formed by removing something from something, not by
Dehydration, dehydration, this is.
Dehydration is dehydration.
Yes.
Can't you also say that for HI, since I like isn't part of the net ionic equation, then it's just H plus that's left, and like from what we learned, H3O
Yeah, yeah, you
plus.
could also just do H plus and then there is no water there.
Yeah. Okay.
Yeah, guys, listen up. Shh, 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 shh. Charles just raised a great point, guys, that further supports what I had said, is that you can also just write this as H plus, not H3O plus, and if you do that, there will be no water there. And in fact, that's how some people prefer to do it. Okay, so sometimes there will just be H plus here, they won't have it attack the water right away. And the H plus will go here, and then there'll be no H2O because it'll just be H plus, not H3O plus. Yes, sir.
What happened to the HI?
What's up?
What happened to the HI? It's in the equation, but there's no, it's in the question, there's no reference of it.
Go ahead, Madison.
So you brought up that you could just write H plus, and which that makes more sense.
And then H plus will attack
So
the
why is
NH3 and it'll be NH4
Why did they write
Wait, where's
H3O?
NH3O?
because they're interchangeable. Like, it's happening, all of this is happening in water.
Where's
So glad everybody.
One second, one
I
second.
as a spectator.
Hello, sister, why are you
No, I'm getting it, but I just.
Yes, yes. I know what you're thinking. We are canceling my substituting.
Can you cancel this class?
Yeah, can we do that? Oh, you just reminded me. I need to yell at Abby.
Oh, wow.
Yay! That's always a good thing.
How do you not know what happened to the HI?
Oh, I
HI is a strong acid. It's on our big six.
Okay, yeah, I know that.
So it won't appear in any. It won't appear in any respectable net ionic equation.
Respectable.
It'll appear.
The video.
Which way, if I find a research paper that has HI, then ionic, would you count that as respectable?
Well, I mean, it's certainly possible if it's not in water, but everything we're doing is in water. It says it right here, molarity. If it has the capital italicized M, it's by default in what, guys?
Water. So
Water.
Yes. What?
Huh?
Sorry. Never mind.
The fear in Victoria's voice. Sorry.
Alright.
The fear in your voice.
What?
So guys,
Do you have scores on your phone?
guys, what has the highest concentrations in the system?
Is your phone recording?
I minus,
I
and
posted and I deleted them immediately.
NH4.
They're each like 4 megabytes of data.
It's never water, right? Like this. Oh yeah, because
Okay, plug those
water
two,
has
you get the point.
And the product
They're
can
huge.
always be
I leaked
referenced
them
as
immediately.
water.
After I put them on YouTube.
exactly.
Oh, you put those.
That's smart. Yeah, how else do you think I was able to post them on Discord?
You should send it on the Discord. I missed it.
It is there.
I did this year.
It's on chemistry.
He's actively just giving up.
Are we ready to move on?
No.
I have a question. So I got the Alec as spectator, duh. But then the NH4 plus, right? So the other concentration is always going to be a product, right? Because that's obvious. Like your product, when you form a product, there's an increased concentration of them, right? And the decrease of like the reactants because they form products. Okay, great. And then it's usually going to be, it's not going to be water because water doesn't have a concentration. So it's always going to be the other thing?
Guys, we still have half the lesson.
How right was that?
We're struggling this much and we only got through half of the lesson. This is the second half.
Alright. Yeah, in previous years I was always done with this lesson by now. Yes, sir.
Do you think like next year's class is getting as dumb or dumber than us?
I think dumber.
I think, truth be told, you guys are not You guys are just fine. There's nothing wrong with you kids. No, listen. Shh. Guys, there is nothing wrong with you. None of you should feel bad. You just had a rough couple of years, and you know, you spent a year and a quarter, so that's like 1.25 school years under siege with, you know, online, whatever. So it's just not the same. It's not as high quality as, you know, in person. And like I said though, you guys will catch up after this year is done. You'll be most of the way caught up because your bodies are just in that catch up mode. But until then guys, you just have to be patient. I know it can be frustrating, especially when people like me don't really help and point out how, oh, we're so far behind and all these grades are so much lower than normal. But you know what, guys?
I have better grades this year than last year.
Anyway, shh. Anyway, guys, long story short, you guys are gonna be fine. You just have to push through. You know, I'm pushing through, so you guys gotta push through. All right. Oops, did I go too far? Okay, here we go. So new example, guys. Shh. New example. Equal volumes of 0.1 molarity potassium carbonate and 0.2 molarity hydrobromic acid are mixed. So guys, this one's kind of a wild one because what do you notice about these two molarities?
There's 2 times the amount of hydrobromic acid.
Okay, and then you guys may not remember this, but carbonate has what charge on it?
2 minus.
So theoretically, if we had enough acid, how many H's could be added to this CO3? You could add 2, right? So that's how we get to this top equation. Now, you guys will not be expected on the AP exam to know the second equation, but you should know it because I taught it to you just for your own reference. Guys, when you have a soda or like a soda stream beverage, what gives it its unique taste? Carbonic acid. What does carbonic acid do when you unscrew the lid or open the pop top?
Allows you to squeeze it over to
The gas, right? So, in this chapter and on the AP exam, you're expected to be able to fill out this first line. But for just general fun and encyclopedia knowledge, what's happening here is what you guys just described, okay? And so, if I place this here, what can I cross out on both sides? Like, we try to add these two reactions together. The H2CO3s. And so, when you conduct this this reaction, it looks like to your human eyes, what does it actually look like is coming off? What does it look like when you're forming gas in a liquidy solution? What does it look like? What does it look like, guys?
Like it's going from the bottom.
Steam.
Bubbles! Bubble. But guys, to our human eye, it'll look like bubbles, but from countless amounts of studying and experiment and stuff, they actually figured out that what is actually being formed first? Carbonic acid. But carbonic acid, does it stay stable, dissolved at room conditions? No, it immediately converts itself into what because of Le Chatelier?
Carbon dioxide.
Carbon dioxide and water. Now the exception to this is if you conduct this in a highly
Pressurized chamber.
pressurized environment, and then it can stay as the H2CO3. Guys, is this second line right here, does it have anything to do with acid-base chemistry? No, it's just something we've seen before, and this is just kind of illustrating an interesting concept where you can mix acid-base chemistry with other stuff. Yes, sir.
Alright, so just so I understand, so what they did is they did CO3 2 minus, which is just potassium carbonate, but since potassium it's only
It's a spectator,
yeah, it's a spectator, so they don't need that. Plus 2 H3O, and because it's hydrobromic, which is 100%
yeah, it would normally just be a 1 H3O plus, and it wouldn't make H2CO3. What would it actually make, guys? HCO3 1 minus, right? But why are we able to make the H2CO3? Because how much hydrobromic do we have?
0.2 mole.
Yeah, so as long as you have more than 1-to-1, you can make some H2CO3. And if you have exactly 2 or more, you can make only H2CO3. Yes?
So if you were to ask us the highest concentration, it would be carbon dioxide and H2CO3?
So here's the tricky thing about that. Is carbon dioxide dissolved right now? No, it's a gas it left.
Right.
So really, what's the only answer? What would the highest concentration be?
H2CO3. But not what?
No, H2CO3 fully turned into these two.
Oh,
So the only real thing would be
potassium.
potassium, yeah.
Okay.
Alright. Equal volumes of 1 molar K3PO4 and 2 molar HBr are mixed. Okay guys, so this is a crazy one. What do you notice? What's right here?
K3.
And we should kind of intuitively remember this, but you can also just figure it out looking at this. What is phosphate, PO4's charge by itself?
3 minus.
3 minus, right? But look, we only have how much HBr?
2.
So we only have how much? A 2-to-1. So we're not gonna make H3PO4. Instead, we're gonna make H2PO4. What? Yeah.
Well, how do you know that?
Because there's only 2 molar, H2 molars compared to 1 K3PO4. So you have
Oh,
two
No.
H's.
What if this said 3 right here?
Then it'd just be H3PO4.
H3PO4 with no charge, yeah. And what if it just said 1 molar?
It'd be HPO4 2 minus.
HPO4 2 minus, yeah. So it's all controlled by how much of this we have.
Will there ever also be like where the volumes aren't equal? Or is it like if the volumes are equal at like or not equal, if the volumes are also like a 2-to-1 ratio, would that just be the same as the molarity being a 2-to-1 ratio?
Well, what's gonna happen is, these are exact integers, right? So what would end up happening is you would just split up the reactions. You'd have up to 3 separate reactions. Yes, sir?
What if, for say, they had 1 molarity K3PO4 and like 1.4 molarity HBr?
Well, that's a case where you would need to have both reactions, and you'd show the first one going to completion, right?
Okay.
And then the second one, you would know would only go 40% because it'd be 0.4. Yeah.
Okay.
So that's why you would still need to have both reactions, because that original product is still going to be there because only 40% of it gets reacted. So it would still have to be represented. So you have to, instead of condensing in a nice clean single one like this, you'd have 2 separate ones.
Oh, makes sense.
And you can kind of see it, I think, in the second homework, where we had the polyproducts and we list all 3 reactions.
You really think I did the second one?
Yeah,
You guys
we'll
are
do
the second
the-
homework.
It's due
Why we
to
just call that space stuff?
But that's why we want one
You're
more
evil
day
for
to
making
do
it
Yeah,
it.
one extra day.
Okay, now guys, this right here is where these what are called polyproduct problems get really tricky. Because they want to know which ones have the highest, and it's here that you start ranking them. Okay, so guys, the K is going to be the most because, what do you notice here? How many Ks dissolve?
3.
So it's like a full 3, right? I just realized I was getting wrong. It's like 3 guaranteed dissolve. So obviously the K is going to be the king, right? The highest. But then HBr goes to completion as well, but it's only 1 of it. Or well, actually, it's 2 of it, right? Okay, and then the HPO4 minus will be the least because there's only 1, and then as far as PO4 guys, how many is there? Just 1, right?
1.
So that makes sense to everyone, this right here?
Yeah.
No, hold on.
Right here, guys. There are 3 Ks, and so when this dissolves, how many PO4s are just dissolved? Just 1. But how many Ks? So that's why K is always going to be the greatest, because it's like a 3-to-1 ratio between the K and the PO4. Okay? And then the HBr normally would just be 1, but what do we have in up here?
2.
So that means it's going to be 2 here, 2 molarity. And then for H2PO4 minus, the PO4 is the chunk of it, right? We said there was only 1 of it, right? So there's just going to be 1 there. Simple chemistry?
Well,
All right, here it is, guys.
This is icy.
Brace yourselves.
oh no.
Well, no, the other ones were icy too.
Well, you didn't need to like actually make it hard. It was mostly
Yeah, the other ones were icy too, but like we didn't really show any of that. But it's just if the weak ones left over. But now, guys, if it's weak, is there any hope of completion?
No.
Correct. So acids and bases will be mostly undissociated. And we write these as proton transfer reactions, where the weak acid is giving what to the weak base? A hydrogen, right? So let's explore what happens when equal volumes of 0.2 molarity aqueous ammonia and 0.2 molarity acetic acid are mixed. So here we go, guys. What's coming off here and going in here? H plus, right? And what's that going to turn NH3 into? NH4 plus. All right, now guys, notice something we kind of subtly threw in here. What do we have right here, guys? It's a double arrow because what did we say up here? So this can't go to completion because there's no strong thing to drive it. All right, anyone need this one still?
Yeah,
Just a second.
So Mr. White, how's your day going?
It's a bit of a roller coaster. I've got something kind of awful brewing over in Mr. White's personal life land. What's that? So I am doing my best. I'm doing my best to hold it all together.
It's always great to take a personal day, Mr. White.
It's just for your mental health. I'm not saying it's for any other reason. And for ours. I promise you, it's just for your mental
Do you still
health.
have all your
No
vacation
other.
days?
Yeah, I've got like 90 saved up.
Just don't come back. Mr. White, after we finish our AP exam.
Actually, I'm sorry, I overspoke. It's 80.
So just don't come to school after AP exam.
Yeah, don't be disappointed in
Oh, but see, here's the thing. Okay, to counter what you're saying, that's like the easiest time for me.
Yeah, that's like the
That's
best time.
true,
It's
yeah.
also the best time for us.
So then just don't come the first 80 days of school.
That's smart.
How do you slip up the
See, I have this weird thing though. Like, I care too much about the mission is the problem. I'm one of those. I'm one of those.
Or just do it every day. The only day you have AP
for the rest
do it.
of the
And then every day you have honors,
Don't
just
come
don't
back.
come.
That's all
Alright,
you
alright.
For your mental health.
So, guys, this is kind of an interesting scenario where sometimes you can throw a cation. Guys, what's the definition of a cation?
Positive charge.
And how can you remember that? What does a T look like?
Plus.
And what's the opposite of a cation since we're already on this topic?
An onion.
An anion. And guys, an has an N in front of ion, and N is the first letter of the word. Okay, that's how I remember the two. Okay. So anyway, ionic compounds containing NH4 plus can acidify solutions. NH4 plus is the conjugate acid of NH3, but guys, are either NH4 plus or NH3 very strong?
No.
No. However, even though, and this kind of goes back to, remember when I first introduced this to you, what did I say? Just because something's weak, does that mean it's not an acid or base?
No.
It just means it can't push it all the way over, right? Still can be very dangerous. So, if we add NH4 and NO3 to water, now why is this important, guys? What did we say about any compound that has NO3 in it?
It dissolves.
So that means you're going to have a full load of NH4 plus. Now the NH4 plus won't really dissociate that hard, but what little bit that does is still able to do what to the overall solution? It can still make it somewhat acidic. So the pH will now drop below 7 because we are increasing the what, guys? The H3O plus concentration, which increases the acidity, yes. But I wanna note though, even though we're saying increases acidity, increases strength, what are we actually saying about the pH? It's going down. Sometimes kids in the heat of the moment forget that, and they'll say, oh, this is a strong acid, which means the pH increases, which, yeah. So I just want to warn you guys about that ahead of time. Who knows, maybe it'll help you remember to not do that.
Can you back up a slide real fast?
Sorry. My bad. I'd say we've been pretty quiet. Yeah.
I think they're
We
done
should
with their
just-
quiz.
Let's scream.
Aren't we supposed to be whispering? I don't know.
Let's not. You gotta use your full enthusiasm.
Huh?
Boy.
Poor
Well, they
man.
don't.
Why do I need a K?
No, I'm thinking.
It's easier for us to learn.
Purple.
Alright guys, let's move on. So, it's not just NH4 plus. You can also have, guys, what does mono mean? The prefix? So monatomic cations can release protons from H2O. And this is because cations can attract the negative poles of H2O. Guys, where's the negative pole of H2O? It's on the oxygen side, right? And there's two poles, technically two negative poles, where the what pairs are on the oxygen? The lone pairs on the oxygen, right? So the positively charged cation decreases the electron density in the O to H bonds, and then that allows some H to escape. And so, guys, if we add FeCl3 to water, you'll have some Fe3 plus, and then that Fe3 plus can get 6 waters to come onto it and say, hey, how's it going? And then it can cause one of those waters that attach themselves to it to lose an H plus. And guys, what is our definition of an H plus coming off of something? If H plus comes off, it's considered an acid. But does this look like, it doesn't look like any acid-based chemistry, but the result is the same. You have an H plus coming off, so this will behave like an acidic solution after we do this. So that's what's kind of interesting. That's one of the things that helped them figure out kind of the whole acid-base thing. What helped them break the case is side investigations like this that show that, hey, look, when an H plus comes off, however it does it, it behaves the same way as all these other ones. Oh, so acids operate with H plus is one of the things that helped them break the case. Okay. So some cations can acidify the solutions as we've been seeing, and the ability to release protons from water will increase as you decrease the ionic radius and you increase the charge. So Fe3 plus is able to do this because 3 plus is a pretty big positive charge, and it's going to decrease it more than Fe2 plus. So Fe3 plus is smaller and it's more able to cozy up to the water and steal some electron density and cause an H plus to jump off. So conjugate acids of strong bases will not affect the pH. So Ca2 plus, Sr2 plus, and Ba2 plus, they cannot change. The same reason that they allowed it to become a strong base is also the reason why they won't affect the pH at all, is because their radius is too large. Alright. We're getting into some weeds here, guys.
I'm sorry, what?
Like, have you ever heard the phrase, getting in the weeds? It's like when you examine something so closely that you go into such detail that now you're wading through weeds. It's like this sort of expression.
No, it's just an example of it.
Well, it's probably because your education up to this point has been so generalized. It's a pretty common phrase when it comes to like subjects where you like really dive down, really dig deep.
Is it a problem that we haven't done that with most subjects, or is that just like a pet peeve of yours?
No. That's just where you guys are. You guys are young. You're in high school. It's mainly in college where you really start digging deep.
How was your high school? Like, are you one of those people that are like, oh, high school's the best time of my life? Or was it like
I
mid?
sincerely hope not.
If anybody says that, I feel bad for them, because dang.
Okay. So it's kind of a strange phenomenon, right? Everyone has a different experience because everyone is themselves different, and then their life experiences are different, right? Like, you know, their home life, whatever. For some people, high school is this amazing gift because they get away from a rough home life, right? For I'd say the vast majority, the vast middle, high school represents this interesting balance between you still are not responsible for most scary adult things, but you are responsible for enough of them to where you've got a sense of independence and you're interacting with other people to where that's where a lot of people, when they look back on it, they think of it kind of, and even some of you or some of your peers will look on this right now as favorably because you've got a nice balance of responsibilities, personal responsibilities, and freedom, right? It's kind of a unique thing. Now, some of you crave ultra freedom, right? You don't like having to ask to use the bathroom or being dismissed by a bell and stuff like that, right? But that's where I'm trying to get at is it's like different for everyone, but at the same time, there's this vast middle that have kind of a similar experience.
So what was your experience?
Mine was like at the upper end of vast middle where I appreciated the relative low amount of responsibilities compared to full adulthood. But then I also kind of wanted to spread my wings even further. Like I had my taste of freedom, you know, so to speak, because it's more free here than it was in middle school, right?
Oh, yeah.
So it's like you get that taste of freedom, and I kind of wanted a lot more.
So you wanted to eat the whole bowl of freedom, not just have a small spoonful.
Yeah, and you know, I want to note though that I generally had a pretty good time. And I want to say especially too, it's like when you get out of 9th grade, especially, because 9th grade's kind of miserable itself.
It is.
Yeah.
Because and you know what?
And Corona hit for us too.
But 9th grade,
My whole 9th grade was online.
9th grade was also great. I'm going to say one thing and then I'm going to get right back to this. You guys are so good at hearing me. 9th grade is good from one sense though. 9th grade is when you're in this high school mindset, you're approaching adulthood. It gives you a fresh taste, a very important taste of what it's like to be the new guy or the new girl. And let me tell you something, it never gets easier. Being the new guy or the new girl is always the tough thing wherever you are. So it's good, it's a good way, it's good that it gets you that, you know, oh gosh, I'm the new kid here, right? It gives you that fresh, you know, start.
I think it depends. 'Cause, like, if you're coming from a feeder, from like, say one of the schools that like sends all of their kids to West Broward, then you at least have like you're not as much of a new kid 'cause you know people.
No, but you still, like, when you get to your electives, there's gonna be bigger, stronger, smarter people who are only these things because they're older than you.
Yeah, I mean,
And they've been here longer. Alright, but I'm here to tell you that it does not get any better. It's like that.
No, thanks.
It's like that at every level. No, but it's good, like,
It's
given
good
that
that-
something's true, it's good to at least know that truth earlier so that you can then learn to cope with it. Alright, so here we go, guys. So some anions make solutions basic. Anions that are conjugate bases and weak acids accept protons from water to produce OH-. So guys, it's kind of the same thing, only this time instead of cations, it is anions. And so the anions, because they're negative, are able to say, hey, H+, come over here, H+. Let's make a neutral.
Candy.
We've got candy and free Wi-Fi.
So-
Don't worry.
These do not accept protons from water because you might notice these are the conjugates of our really. So these will not do what this slide is saying. But many other anions will. And it's just simply because they want to pull that positive thing over to them. So acetate is a real interesting one. When you add acetate to water, it's going to actually make the water more basic. And remember, acetate is the conjugate ion of acetic acid, which is vinegar. It's going to pull off an H off of water, and it's going to make water have a little bit more OH minus. And when you have a little bit more OH minus, what does that make your solution, guys? Basic. All right. So the sulfate ion is a very weak base. However, if you add it to water, you can get a nice, very small change in pH. All right, metal oxides are basic, and that's because O2 minus, and I want to note these don't dissolve very well in water, but when you can make them dissolve a little bit in water, the O2 minus will steal some of the H from the H2O, and guess what that's going to make, guys? OH minus. And guys, by that definition, what happens when you have more OH minus? You get more, even if it's just a little bit, you get more basic. So this slight solubility of the hydroxides allows you to increase the OH.
Wait, hold on. I was still writing that down. You're going really fast, Mr. White. Jeez.
Well, because this is the region of slides where it's more like just straight up information.
I know, but like still, it's not like it isn't like anyone's recording this stuff for future reference.
Yeah, I know, right?
Yeah, that would be crazy.
That'd be terrible.
Definitely.
Who would do that?
Definitely off the wall.
What?
It's all recording.
You kids, I love you
No,
guys.
his philosophy.
Well, it's
Next-
kind of weird, Mr. White.
Nice phone, Michael.
Yeah, it's pretty cool, isn't it?
He is a, not a minor, he's a major.
He's a major.
That's
What?
My own.
He's supposed to.
Oh my god, I'm thinking like everything I said is like on recording.
So out of pocket.
I asked it, I was supposed
Wait, what happened?
to. There was an equation with carbon dioxide and water. And I was like, photosynthesis.
Wait, what? Wait, you got a bubbly thing?
Definitely got
I
that.
asked him if it was photosynthesis.
We really had
I do not know how fast it works.
Alright, guys. Oh, you're still writing? No problem.
I'm almost done. Give me a
You're
second.
fine, you're fine, you're fine. I still love this drawing. Remember this? This was so cool.
Yeah.
I was gonna mention that drawing was like a sad face, like
It
like the hair,
represents
and then
something
like it looks like it's crying.
Like a monster sad face?
No,
Like-
it looks like it's crying.
Mr. White, have you seen Spirited Away?
The arrow on the bottom slightly curved.
No,
Yes, I have.
It looks vaguely like No
We're not
Face.
gonna be an AP Cat Marco.
Alright, shh, 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 shh. Here we go, guys. Let's look at an example. We put potassium oxide in water, and what's gonna happen here, guys, is it'll dissolve, and you'll have some O2 minus. And then, guys, what's the O2 minus gonna do with H2O? It's gonna make more OH minus. And so then, it's the same thing. We can add these two equations together, like we've done many times this year, and get this overall equation. And so, by adding solid potassium oxide to water, you can actually make it more basic. Yeah.
Wait, that equation isn't balanced. There's 3 oxygens on one side and 2 on the other.